Hi, the last modulator we will talk about is the pitch. This modulator analyzes an input signal's pitch and produces a modulating signal based on that. The first application that comes to my mind is a tracking pitch equalizer. For a successful job, the input should possess a distinctive, i.e. well-defined pitch and being monophonic. Neither chords nor intervals. Also, no effects, delays, reverb, chorus, etc. Think solo synth, bass line, or single vocal. Because finding a source's pitch is the first and most important task, a detector plays a crucial part here. So let's start from it. I'm going to use the M-Auto Dynamic EQ to demonstrate the detector's work. The first thing to understand is the detector produces modulation for an entire 20 Hz to 20 kHz frequency range. That means if you want the filter to track the pitch correctly, you must set 20 Hz to 20 kHz range for a filter as well. That is, even if an input signal has 440 to 880 Hz range, and you want the filter work between 440 and 880 Hz as well, you must still set the filter's range to 20 Hz to 20 kHz at the parameters panel. For the demonstration, I'm going to use simple sine wave, whose pitch changes in octaves. If, for instance, I set it to 20 Hz to 1 kHz, I'll displace the filter's range towards 20 Hz. Likewise, if I set the range to 100 Hz to 5 kHz, I'll shrink it towards the center. As you can see, any deviation from 20 Hz to 20 kHz range leads to errors in the filter's tracking. Two controllers at the top, min and max frequency, do the opposite job, i.e. they stretch the filter's range. Respectively, if I put the same values for the min frequency and value, max frequency and maximum value, shrinking and stretching will cancel each other out and our filter will be back on track. Now, to detector's parameters. To open the detector's panel, click on this button. Min and max frequencies set a range the detector will react to. These are not set and forget parameters as they may seem. And here is why. Listen to this FM piano part and watch for the filter's movement. As you can see, on some notes, the filter jumps over too much lower frequencies than the actual frequencies of the notes. To avoid it, I must set the min and max frequency controllers to the range of the piano's fundamentals. In such a way, the detector will analyze only necessary frequencies, not the entire range, and by doing so, I diminish the probability of an error. Remember, the detector has no idea what it should consider as a useful signal. It will analyze everything you throw at it. So, it's your job to cut this data down up to a necessary part. In my example, all I'm interested in is B5 to G#6 notes. That gives me 493.9 to 830.6 Hz range. And see how the filter moves after I enter these values. No errors at all. The speed parameter defines how fast a modulation will take on a new value when a pitch changes. See what's happening when I'm lowering the speed parameter. The lower the value, the slower the filter's movement. And vice versa. At 100%, the filter tracks notes almost instantly. The stabilization sets the time during which any change in pitch will be ignored. Handy if you're dealing with a signal that has small pitch variations and you don't want the modulator to react to them. I'll use the previous example, however this time those long notes have short fluctuations. Right now the modulator is tracking the pitch precisely, but as I'm increasing the stabilization, the modulator starts ignoring the fluctuations. The downside of this feature is it introduces a sternness to modulation. Watch the filter's movement at slow speed. The higher the stabilization, the more step-like the movement. The accuracy determines how exactly the modulator detects the pitch at the expense of CPU usage. The threshold is one more parameter to help the modulator to define the useful data. Signals with lower level than this won't be considered. As a reference, use the input meter of the plugin. The Auto Tune panel holds the automatic tuner parameters. It doesn't alter an input signal's pitch in any way. It simply quantizes the incoming pitch to the closest note on the equal temperament scale. The speed defines how quickly the algorithm tracks the pitch. The depth sets how exact the resulting pitch will be. To me, the auto-tune is a good alternative to the stabilization feature. It quantizes the pitch as the stabilization does, however, it doesn't distort a modulation signal. All right, I think we've learned enough now to use our knowledge for something useful. In the following example, I'll apply the pitch modulator to fix FM piano's timbre. Here it is. It sounds a bit harsh to me, especially when it plays higher notes, like here. To fix that, I'm going to use a high shelf filter that will follow the melody. Plus, its gain will depend on played notes. As usual, I start from assigning parameters to a modulator. The frequency range is 20 Hz to 20 kHz, and the gain is to some arbitrary value. Next, I need to define the min-max frequency and threshold for the detector. For that, I simply play back the piano's part and make notes. If you have a MIDI track, you could simply check the lowest and highest notes and put them as min-max frequency parameters. Anyway, the range I have here is B5 to B6. That's approximately 490 to 1000 Hz. Done. The signal level is within -10, -15 decibels. That suggests to me that if I leave the threshold as its default level, it'll be fine. Besides, the piano part is pretty clean in terms of noises, so I don't have to be too fussy about it. I'll leave all other settings at their default values as well. Great. Let's hit the playback and see how the filter works. Not bad. First thing to notice is the cut frequency is located much lower than I need. I can't simply change the value and maximum values in parameters as I would with other modulators. We already know that it'll falsify note tracking. Instead, I'll resort to the shift panel. It does exactly what I need, shifting the cut frequency. After some experimentation, I've ended up with these values. All what's left to do is tuning the gain parameter and going through the detector's residual parameters. Here is the final result. In the bass guitar example, I used M-amp and M-multiband harmonizer to add extra harmonics to the instrument's low notes, so it sounds more pronounced at lowest notes. Let's start with M-amp. I pointed the pitch to the drive controller. Next, I figured out min-max frequency and threshold for the detector. The rest of the parameters were set by trial and error. The extra part that deserves mentioning is the transformation shape feature. I had to use it to shift the drive's value to 0 when the bass plays high notes. In M-multiband harmonizer, the format shift works in such a way that when the bass plays low notes, the formants are shifted higher. And when the bass plays higher notes, the formants are shifted lower. It helped to improve audibility of the bass's low notes even further. In the detector, after min-max frequency and threshold was set, I experimented with the modulator's min frequency and max frequency controllers to obtain the format shifts behavior that I wanted. Again, I had to make use of the transformation shape panel, and here is how it sounds. Basically, that's all. You can use this approach to modulate anything you want, really. Try every parameter, apply transformation shapes to link them in some unique way. So here we are, with all 5 modulators at our disposal. It's been a long and sometimes difficult journey, but we've learned so much. Modulators considerably spread out boundaries of our creativity, and we've learned that they can turn a reverb into a percussive machine or an equalizer into a phaser effect. Just use your imagination and I'm sure you'll come up with some great and unusual ideas. Some of you can say that the same can be done with VST automation. Well, not really. Yes, one can control plugins parameters via VST automation, but not as effective, comprehensive and fast as by the modulators. I feel like we are at the beginning of something new in music production. All the best.